Recording, and I still have not had a chance to put the recordings online, but I will get to that as soon as possible. And share. Okay. So last class, we started talking about determinants. And if we remember, when we have a matrix A1, B1, let's do that's A1, A2, A3, B1, B2, B3, C1, C2, and C3. Okay. Then we can take the determinant of this matrix, which we write in straight lines. We put these coefficients between straight lines, A1, A2, A3, B1, B2, B3, and C1, C2, and C3. And what we do is we go to our first coefficient over here, and we put that here, A1. And then we put the matrix, the results from crossing out these two lines. So that would be the matrix B2, B3, C2, and C3. And then we do minus, and we go to the next coefficient in line, which is A2. And we put that A2 over here. And then again, we cross out these two lines and we get the determinant of the resulting matrix, and we put that over here. And that is B1, B3, B1, B3, C1, and C3. And then we put plus, and we go to the last one, A3, and we put down the determinant of the matrix B1, B2, C1, and C2. Any questions so far? Okay, and then we take the determinant of these matrices. So this will be equal to our A1 times B2, C3 minus C2, B3 minus A2 times B1, C3 minus C1, B3 plus our A3 times B1, C2 minus C1, B2. And this is a number, and that number is going to be the determinant of this 3 by 3 matrix. Any questions about this? Okay, so in a similar way, we can take the cross product of vectors. So if you have the vector V, which is equal to V1, V2, and V3, and you have the vector W, which is equal to W1, W2, W3. So these are two vectors. You can take the cross product V cross W, and what you end up doing is you take the determinant of the matrix that goes, you put in the first row I, J, and K. And then in the second row, you put your first vector, V1, V2, and V3. 1 second. Okay, V3. No. I might have to close a couple of pages to get this to work faster. Yeah. So let me stop sharing for a second. Okay. Let's see if this works better. Okay, so let me try going to a different. Try closing more applications first. Okay, perfect. Okay. So then in your second row, you put V1, V2, and V3. And if you guys are confused about what is a row and what's a column in a matrix, the columns you can think about as like columns. So they are these stuff over here, like a column. So it goes from up to down. And then the rows are just, a row. So that should help. And then for W, you put W1, W2, and W3. And then what you do is you now take the determinant the way we took it before. So you put your I over here, and then you take your matrix. So then you take the determinant of the matrix V2, V3, W2, and W3. And then you go minus, and you go to your J, you put your J over here, and you put the determinant of the matrix V1, V3, W1, W3, and then plus K, and then the matrix V1, V2, W1, W2. Any questions? Okay, and then you just open this up. So now you're going to take the determinant of each one of the smaller matrices. So this is going to be I times W times V2 W3 minus V3 W2 minus J times V1 W3 minus V3 W1 plus K times V1 W2 minus W1 V2. Okay, we can write these in their components. And so we get the vector V2 W3 minus V3 W2 and then a minus sign in front of this whole thing, V1, W3 minus V3, W1. And lastly, in the K component, we get V1, W2 minus W1, V2. So in other words, the cross product takes two vectors and outputs a vector. So we can say it takes a vector and another vector. And as an output, it gives a vector. That's what the cross product does. While the dot product takes a vector and you dot it with a vector and you get some real number. So that's one difference between them. Any questions? Okay, so here's the formula we just saw. And all you really need to know is how to do the two-dimensional determinants, and then how to do this trick with I, J, and K, and now you can take a cross product. So they give you this following example. Find the determinant of, okay, let me do that somewhere else. V is negative 2, 1, 4, negative 2. V is equal to negative 2, 1, and 4. W is equal to 3, 2, and 5. 3, 2, and 5. 3, 2, 5. So they ask us, what's the cross product of V cross W? So that's going to be the determinant of the matrix I, J, K, negative 2, 1, 4, 3, 2, 5. And this is going to be, why don't you guys take a couple of minutes and do this cross product, and then we'll do it together. Okay, so let me do it. So the first component will be I times the determinant of the matrix 1, 4, 2, 5 minus J times the matrix negative 2, 4, 3, 5 plus the matrix, or the determinant of the matrix, plus K times the determinant of the matrix negative 2, 1, 3, 2. And so then this is going to be equal to I 1 second. Yeah. 5 minus 8 minus j times the determinant of this matrix, which is negative 10 minus 12. So that's negative 22 plus k times negative 4 minus 3, which is negative 7. So then this is going to be negative 3, 22, and negative 7. Any questions about this? And you get a vector in the end. So you get this vector in the end. So you take two vectors, you take their cross product, and you end up with a third vector. Okay, so the same way the dot product had certain geometrical interpretations. One of them is that it's related to the angle. That's its main geometrical interpretation. And we had, if you recall, the formula that the angle between two vectors is equal to cosine inverse of those two, the dot product of those two vectors over their divided by their magnitude. And that was some geometrical interpretation that we had for the dot product. The cross product also has some geometrical interpretations. The first one, and probably the one that's used the most often, is that the cross product of two vectors is orthogonal or perpendicular to those vectors. And that you can see in this picture. Here's V, here's W. U over here is V cross W. And it's orthogonal to V and W. And if you want to know which direction it's going in, so if you have two vectors, V and W, and you take their cross product. Now the cross product if it's orthogonal, it can either be going in this direction or it can be going in this direction. And sometimes we would like to know exactly which direction it's going in. So what you end up doing is you take your right hand, you put these fingers in the direction of V. You put the back of your hand in the direction of W, and the direction that your thumb is pointing in, that's the direction in which this vector is going in. So in this case, it's coming out, because if I do this, it's coming out. And this is V cross W. So because V is coming first, so this is for V cross W. So because V is coming first over here, your index fingers are going in the direction of V. Now, if you were looking at W cross V, then we're doing the opposite thing. We're putting our index fingers in the direction of W, the back of our hand in the direction of V, and now your thumb is pointing downwards, so you know that the vector is pointing downwards. Any questions about this? It's called the right-hand rule. Some people use this finger and this. I prefer what I just said, thumb and your index finger. I mean, back of your hand and your index finger, okay? Okay, definitely play around with it. Make sure you understand how it works. So over here, you can kind of see that picture here. These fingers are mostly pointing in the V direction or like closer to the V direction. You just have to put this in the W direction, the back of your hand, and your thumb is pointing outwards. And so that tells you the direction in which this vector V cross W is pointing in. And like we said, it's orthogonal to both V and W, which means if you take the dot product, then of course you can, because V cross W is a vector. So if you take the dot product of V cross W dotted with, let's say, V, what would you expect to get? Anyone? Zero, right? Because they're orthogonal. And if you want to know if two vectors are orthogonal, you take their dot product. Any questions about this? Okay. The second most important property of the cross product is fairly similar, and so it should basically be remembered in a very similar way to the one for cosine, that the magnitude of V cross W, and they say the length, is equal to the magnitude of V times the magnitude of W times sine theta. So now we have one rule that compares the dot product with cosine, right? And it says that V dotted with W is equal to the magnitude of V times the magnitude of W times cosine theta, cosine of the angle between them. And now we have another rule that says that the magnitude of V cross W, and the reason we need a magnitude is because this side is a constant, magnitude of V, magnitude of W. So we need to have magnitudes, we need to have some length. We can't have a vector here, but this is equal to the magnitude of V times the magnitude of W times sine of the angle between them. Okay, so that compares, so now we have a relationship that compares the dot product to cosine, and it compares the cross product to sine. Okay, and that's just important to remember. And of course, you can use this formula to also find the angle, though I would not recommend it because it's always easier to find the dot product, or generally it's easier to find the dot product than the cross product. But you can say that the angle is also sine inverse of the magnitude of the cross product of your two vectors divided by the magnitude of V times the magnitude of W. And this again is if you're trying to find the angle between V and W. Now, again, I wouldn't recommend using this formula if you're asked to find the angle, because this would require first taking the cross product and then taking its magnitude, and it's always easier, generally easier, to just take the dot product. Any questions? Okay. And this property we already spoke about. These three vectors, VW and V cross W, create these three vectors that you see over here, V, W, and V cross W, and they call that the right-hand system. So you don't have to remember that name, but you should remember that when you take the cross product of V and W, you get a vector that is perpendicular to both V and to W. And if you want to know in which direction it's going, you use the right-hand rule to know in which direction it's going. Okay, any questions? So let's go back here to what we saw V cross W be. And that was right over here. This was the vector that we obtained, the general vector that we obtained. Okay, the general vector that we obtained when we took V cross W over here. And like I said, if you want to verify that these things are perpendicular, what you do is you take this vector, and this is the vector V cross W, and you say, okay, what is V cross W dotted with V. Okay, so what is this? This is going to be equal to, in the first component, you get V1 times V2 W3 minus V3 W2. That's what you're going to get from the first one. Plus V2, so now that's the second component, times this over here, which is going to be, so I'm going to just distribute the negative. So we're going to get V3W1 minus V1 minus V1 W3. Yeah? And then plus, and then for the third component, we multiply the whole component by V3, right? That's what it just means to take the dot product. So plus V3 times V1 W2, V1 W2 minus W1 V2. Okay, so V1 V2 W3 can be erased with this one, V1 W3 times V2. So those two cancel. Then V1, so this V1 minus V3W2, so V1, V3, and W2, V1, V3, and W2 cancels with this over here, because that is negative. It has a negative, and this is positive. Okay, and finally, the last one is this one over here. V2, V3, W1, V2, V3, V2, V3, W1 minus. So you get 0. Okay, does this make sense? So when you take the cross product, V cross W, and you dot it with either one, either with V, or if you take V cross W, and you dot it with W, you get 0. Which shows that they are in fact orthogonal. Now, because of the right-hand rule, we can see that the cross product is not commutative, because when you have, let me draw a picture here. When I have here V, and here I have W, so I know that this vector, by the right-hand rule, so I know that this vector here, by the right-hand rule, is V cross W. Right, I put my index fingers in the V direction, the back of my hand in the W direction, my thumb is sticking upwards, so it's going upwards. And I know that this vector is negative. Well, first I know that it is W cross V, right? Because now your vector is going in the opposite direction. You're putting your index fingers in the W direction, the back of your hand in the V direction, and your vector is going down. But I also know, if I look at these two vectors, that there is some relationship between them. And that's that this vector is the negative of the V cross W vector. Because that's what happens when you take the negative of the vector. The vector flips. And so now we have this relationship. That W cross V is equal to the negative of V cross W. Okay, let me leave this and start another whiteboard. Any questions? Yes.
The property where V cross W is equal to the magnitude of V multiplied by magnitude of W multiplied by sine of theta. Isn't sine of theta always going to be 1 because it's orthogonal?
I mean, there isn't, you're not taking like a dot product. This is the angle between V and W, and they're not always orthogonal. So it's the sine of the angle between V and W. But, and that's, you know, some vector, but not necessarily orthogonal. The orthogonality is between V and the cross product of V and W. So if here's V and here's W, this is the angle between them. That's, for that we have the formula, the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times sine of the angle between them. That's for this vector. The resulting cross product is orthogonal to both of them. So you see it's perpendicular over here, and this is V cross W. But it doesn't appear, that angle doesn't appear in this formula. Any other questions? Okay. So that gives us this formula over here. W cross V is equal to negative V cross W. And so then you get some of these properties. So the first one is what we just saw. Can anyone tell me a good intuition for the second one? An intuition or, yeah.
Same vector, the angle between them would be 0 since sine of theta is 0.
Exactly. So you can just use that formula and you figure out the second part. Another thing that is interesting to note is if you have the same vector, there really isn't a good way of talking about the angle that's orthogonal to both of these. This might be orthogonal to both. There's an entire disk over here of angles that are orthogonal to both. And that, of course, doesn't really make sense. So you get 0. That's another way of thinking about it. Okay. And then the rest of these properties just follow from the definition of the cross product. And you actually don't have to memorize them. They don't appear that often as important properties. And so there's a lot to learn, and we will skip some of the stuff that is not completely useful. We also have these relations, which you can figure out yourself by just knowing the rules that we currently talked about for the cross product. So the cross product of I and J, well, it should be a vector orthogonal to I and J, and the only vectors that are orthogonal to I and J are either K or negative K. X, Y, Z. So here's your I, here's your J. And if you want to know which one it is, it's either K or it's negative K. Okay, so you put your index fingers in the direction of I, the back of your hand in the direction of J, it's pointing up, so it's going to be K. So the cross product of I cross J is equal to K. And the cross product of then J cross I, well, because of the rule that we just learned, this is the negative of this cross product, so we know it's negative K. Or you can just try the right-hand rule again, put your fingers in the direction of J, the back of your hand in the direction of I. Now your thumb is pointing down, so this is negative k, because k is pointing upwards. And the rest of these rules follow in a similar way. Okay, I'm going to skip this physics problem, but as you can see, it uses the formula with sign that we just talked about. And if you know anything about forces and vectors, you should be able to do this problem. Torque is something that I do want to talk about. So let's try to do this problem. And in this, and by the way, torque in general is a cross product, if you've seen it in physics. So they tell us that you have a wrench like this, and you're trying to turn something, and you're applying a force on it. So here's your force, and you're applying it some radius away. And that's generally what you need for torque. So they tell us the torque is given by R cross F. That's just what the torque is. And F is the force being applied, and R is the vector away from where you are applying. So you're applying the force here, and you're trying to find the torque over here. And so R is this distance vector. Okay, so they want us to compute the torque in each case. And if you've seen, for example, these wheels that are spinning, and then they start moving in the, like you have X and Y, for example, and now they start moving in the Z direction, suddenly there's some force in that direction. The reason that force appears is because that the torque is always orthogonal to, for example, here R and F. So the force is going to be coming out like this, which is a counterintuitive thing. But that's again because we're taking the cross product, and the cross product over here will be orthogonal to both R and to F. So they want you to compute the torque in each of these cases. If the force is this and R1 is this, or if the force is this and R2 is that. So here's one case, your force is being applied over here, this distance away. Second case, your force is being applied here, and you're that distance away. Okay, so what you want to do is you want to say my torque is R1 cross F1. That's just what my torque is. And then you just need to compute that cross product. You can use the rule that we saw. You can take a matrix. In this case, it's fairly simple. They're trying to use rules that we're not going to look at. So it is easier to just try to compute the determinant of the matrix I, J, K. And then in the first row, you put 0.5, 0, 0. And in the second row, you put 0, 60, 0. And once you compute this, you will get your torque. Now, a little trick that you can use over here is because that everything, you know that your forces only appear in the K direction. So you can actually ignore the I and the J. And in fact, if you take those determinants, you get 0. So let's try it. I times the determinant of the matrix 0.5, 0, 0, 60. Oh, sorry, that's the K one. And that actually does get us to some number. And we'll see that in a second. But let me erase this. Okay, I times the determinant 0, 0, 60, 0. Well, this, of course, is 0. 0 times 0, 60 minus 0, whatever. 6 and minus 60 times 0, that's 0. So in the I component, you get 0. In your j component, you're taking minus j times the determinant of 0.5, 0, 0, and 0, which again is 0. So you get 0. And then in the k component, you get plus k times the determinant of 0.5, 0, 0, 60, which is 30. So now you know your force. It's going only in the z direction, which makes sense because your forces are being applied in the x and the y direction. And it is 30 newtons in the z direction. Any questions? So once you know about cross products, it's actually fairly easy to find the torque of different vectors, the force vector and this distance vector. And it's also fairly intuitive. I wouldn't say intuitive, but it then makes sense that this force, even though the force is being applied here, it's being felt like that for some reason. Okay. So the last thing I want to talk about is how the cross product connects to area. And so for the dot product, there are two important things that you can do with the dot product. You can find an angle and you can find a projection. Those are the two main important things that we want to do to use the dot product for. And the formula for a projection, as we said, using the dot product, u projected onto v is equal to u dot v over the magnitude of v times the unit vector in the direction of v. So those are the two important things with dot products: angle, projection. The two important things for cross products are to find vectors that are orthogonal to two other vectors. Very important. So if you have two vectors and you want to find the vector orthogonal to them, immediately you should think about the cross product. That's number one. Number two, to find either the area created by a triangle formed by two vectors, so this area over here, either that area or the area of the parallelogram formed by two vectors. Or in other words, finding areas. So again, two important things: finding normal vectors or orthogonal vectors, and finding area. Okay, any questions? So we might ask, why do we use the cross product to find area? And the answer is because of its relationship to sine. So the same way that the relationship that the dot product had with cosine allows us to find angles and allows us to find projections, and we talked about why that was, the relationship that the cross product has with sine helps us find the area of a parallelogram. So here's an example. If you have these two vectors, v and w, that you see in this picture, well, v cross w is orthogonal to them and pointing out. And we have this relationship that the magnitude of v cross w is equal to the magnitude of v times the magnitude of w times sine of theta. Now, sine of theta is this height over here, this h. We know that the area of a parallelogram is its base times its height. Basically like a square, but it's harder to find the height with a parallelogram because you're not given it. So you want to find the height, but that's this area. Well, what is that? So your base is your vector v. That's your base of your parallelogram, v, or the magnitude of v, I apologize. So that's your base. Now your height, well, your height is the same as y r. So your height is y. If you can imagine putting your parallelogram in the xy coordinate plane. So now your v is here. Here's your parallelogram. This is your w. Your height is y. This is y. That's your height right over here. Y of the y component of w. So what is that? If I take the magnitude of w times sine of theta, I get my y, right? That's what sine does. It projects w into the y direction because y is equal to the magnitude of the vector w, which is this magnitude of w, r sine theta. That's what y is. Again, I would recommend memorizing the formulas. X is equal to r cosine of theta. Y is equal to r sine of theta. Very important formulas in this class that will appear multiple times. Okay, so if y is w sine theta, what we can say is that your area, which is your base, which is the magnitude of v, times times y, which is your height, would be the magnitude of w times sine theta. But we know what this is. This is the magnitude of v cross w. So the area of the parallelogram formed by v and w is v cross w. Okay, if you have two vectors and you want to find the area of the parallelogram that's formed by them, v cross w, the magnitude of v cross w. And the area of the triangle, so if you're ignoring half of it, well, that's just half. So that's why you divide by 2. We're going to stop here. If anyone has any questions.